shape looks an awful lot like that shape. But if I show you the motion history image of the one on the top, you see that. And you can see that it's dark down here and light up there. So that's an example that the arms are moving upward. When you take a look at this one, you can see that it's high up here, but high down there. So it's actually going like this. So the motion energy image would be ambiguous. It shows you where the stuff is, but the motion history image resolves that ambiguity. The motion energy image captures the whole image motion area and captures it nicely, so that's why it's not in some sense redundant with the motion history image, which gives a lot more weight to the more recently moving pixels. So here's an example of 18 different moves, and it's showing you some of the motion history, motion energy images of it. So we now have this problem of how do we recognize motion energy, motion history images? Well, these are kind of grayscale, blobby-like images. And the good news is, even in 1999, there had been about 150 years, or maybe 20 years, pick your favorite number, of computer vision describing gray blobs and trying to say, okay, I recognize this gray blob as being different than that gray blob. And that's basically all we had to do. So basically, in 1999, we did some sort of what I think of as old-style computer vision. We're going to compute some summarization statistic of that blob. We're going to compute some features of that blob that have something to do with the distribution of where the pixels are and their intensities in the MHI. And we're going to build a generative model. Okay? There are a couple of reasons we were doing generative models. One is that discriminative models hadn't become as popular as they had been, and so Jim Davis's advisor was not smart enough to tell him to go make sure you use a discriminative model. I will tell you that people have subsequently used it, and of course it makes your recognition better. Generative models also have the nice property, as we mentioned before, that when I come in, if I come up with a new aerobics move, right? So I want to add one. I just have to build a model of that category. I don't have to retrain my entire system, okay? Whether you use generative or discriminative, the idea is that we're going to compute these statistics and then do the recognition. So how are we going to describe these things? And this allows me to spend a little bit of time telling you about some very old computer vision work that's still important and fundamental. And that's the notion of the moments of a shape. So some of you from physics, you know about second-order moments, right? Axis of inertia. The moment is the distribution of matter about a point or an axis or something like that. So in computer vision, the moments are defined in a very simple way, right? So the ij moment, okay, is just the sum over the xy of the whole image of x raised to the I power, y raised to the I power, but you're only counting points where the image is non-zero, okay? So if I is a binary image, then this is a 1 or a 0, so you're only counting it at points that are turned on. If it's a grayscale image, then you're weighting the point by essentially how heavy it is, which is a little bit like when you do moments of inertia. If you've got little points that are heavier than others, they add more to the inertia about the axis. So these are the moments, and so you could talk about the second-order moments or the first-order moments or even the zeroth-order moments, right? What would this be for the zeroth-order moment? Well, if I is 0 and j is 0, then these are 1. This would just be counting up the number of non-zero pixels, which means that M00 is the area. Ooh, right? Because the area of the picture that's non-zero, that's just the sum, it's the counting of the non-zero pixels, all right? The problem with regular moments, of course, is that they're sensitive to what the x and y position actually is, right? So you kind of want the moments of a shape to be independent of where the shape is. So there's something called the central moments that just take x, but they subtract off the mean of x and y and subtract off the mean of y. And it is otherwise just the same. So that's this mu pq, and it's x minus x bar to the p, y minus y bar to the q. All right? And, you know, what is x bar? Well, one way of thinking it's the average x. So the average x would just be the sum of all the x's divided by however many x's there are. Well, that's what this is, right? X bar is M10, the first moment in x, divided by the overall area. Remember, the m00, same thing in y. So that's regular moments. But the problem with moments, of course, is that they're very sensitive to a variety of changes. So if I scale the image up, right, obviously the moment's going to change. The area will get bigger, the distances get larger. If I rotate it, things might change. All sorts of problems. So there was this guy named Hugh, and he created a set of moments. And what was really cool about the moments that he created is that they were rotation, translation, and scale invariant. And you see I put scale in green here because for what we're about to do, the translation part is taken account by just using central moments. We don't really need rotation invariant that much because people don't tend to do their aerobics at a 45-degree angle. But we do get scale differences, right? If things are closer to the image or closer to the camera or farther from the camera, things get bigger or smaller. So we want to create some descriptors that are invariant. And Hugh moments are of that type. And we're going to use 7 of them. And that's what these 7 Hugh moments are. And I'm going to show you the equations for them. You would never write these down. You would go get an implementation of them because otherwise you'll make a mistake, etc. But here they are, okay? And in fact, they're so ugly that they don't even all fit on one page. So you see it says this is H1, and that's mu20. Remember, mu are the central moments, okay? Plus mu02. And then they continue H6, and then H7 is even more ugly. There they are. They're just that sort of complicated, ugly thing. All you need to know is we now have a translation and rotation and scale invariant system. So the details of what the features do are not that important, except that they behave the way we want them to behave under particular types of transformations. What matters is I'm going to compute these features on both the MEI and MHI, so the binary version and the grayscale version, and that's going to give me a feature vector. And given a feature vector, I can build classifiers. So remember generative versus discriminative? So generative, I build a model of each class, and then I compare it against all of them. Discriminative, I build a model of the boundary between the classes. So we've talked a bunch about building some discriminative one. Let's talk again about building generative. How might you build a reasonable generative model of each class of action? Okay. Well, remember, one of the reasons we might want generative models is we might not have a whole lot of examples. So a simple thing you might do is you've got a Hugh moment feature space, and we've got 7 things applied to 2 images, so we get 14 numbers. So you could use some sort of Gaussian, or maybe it's a Gaussian with diagonal covariance so that you don't have to worry about having too many points. Or you might use a small number of multiple mixture of Gaussians, but the idea is you would build a model, a Gaussian model for each of those classes. And then what you'll do is you compare the likelihoods. Remember, the likelihood was probability of the data given the model, right? So I build all the models, and then when the new data comes in, I evaluate the probability of the data. Then if I have a prior, then what I'm going to do is I'm going to use Bayes' rule. That's what it says here. That basically says I take my likelihood, I multiply that by the prior of my model, and that's proportional to my total posterior. If I don't have a prior, I might just select whichever one has the highest likelihood. And by the way, if I don't have enough data to even build some reasonable model of the densities, I might just use something like nearest neighbor. So the nice thing that we have is that the motion energy images, motion history images, they're sort of little global descriptors. And the way you do this is you're going to collect these statistics on these global descriptors in order to do the recognition. One of the things that might be a little less obvious is you can't actually recognize the action till it's done, right? So I have this description that goes back in time. So if I'm watching a person sit down, when they're done sitting down, I now have that chunk of data that represents them sitting down. Most activity recognition these days, there's not a lot of focus on doing online recognition that as you're watching something happen. The idea is that they have the whole sequence to begin with. But if you actually are worried about recognizing it as it happened, this idea that I can't recognize something till it's totally done can be somewhat concerning, and you have to think about how you might deal with that. A couple of cool properties. As we said, that this does, it's very easy to construct the MHI for one tau from the other. So you can go from tau 30 to tau 15. And that's basically a linear scaling, right? So if I have an action that can go fast or go slow, that's okay. It's not okay for an action that goes, the first half of it is fast and then the second half is slow, where I have to do something more serious, some more serious dynamic time warping or something like that. The whole idea is that we have these atomic primitives that can be performed quickly or slowly, but they don't have lots of parts to them. It's recursive, so it's very fast. What's interesting is, and I've had conversations with some people who do work in vision from the neural side or from computational vision from biology. You could imagine building something like these MHI detectors from very simple neural hardware, basically filters with slow responses. And the fact that these can work from very low resolution images, which I haven't shown, but because it's just a global pattern, you don't need a lot of pixels. It means that out here in your peripheral vision, where you have hardly any resolution at all, when we do the human vision lesson, we'll talk about how you think you can see out here, but not really. You're just making it up. All right. But what it means is with very low resolution, you can recognize things. So I'm not going to claim anything in terms of biological reality. I'll just say that there's some biological plausibility to this kind of work. And there's a reference in PAMI which sort of talks more about this. We actually use this system to build a couple things. Here's Jim Davis when we were both much younger, building a aerobics system where you would be taken through aerobics by the system, and it would watch you, and it would know which aerobic you're doing. I mean, which one you're supposed to be doing. It tells you, so it could recognize it. It was real easy. We did have this cool little thing that the music, and Jim was very clever in making this happen. The music was actually MIDI controlled, so we can control the tempo, right? It wasn't just pre-recorded. So that means we could watch you, and we could always make the music go just a little faster than you're going. So we could sort of just play with your head and speed you up and make you sweat more. But it was cool that the thing would just recognize the system. A more compelling use of this technology, we built this thing called the Kids Room, and it was an interactive play space for children. The original intent was to just illustrate how computer vision could do some interesting, cool stuff. And what was interesting is a nice article about it in Presence, but some folks came by. I don't remember exactly how it was that they were at the Media Lab, but they really liked it, and they ported it to the Millennium Dome. So they built this big thing called the Millennium Dome in London at the turn of the century, at the Millennium. And they had all these pavilions, and they were looking for interesting technologies, and this is one of them that they put in there. So I have a little video here that shows you, first of all, temporal templates being used. So the monsters teach the kid these moves, and then, which is good because if we wanted to, we could actually get training data from the actual kids that were there, but the system was robust enough that we could use training data from just a couple of people that we trained on, and it would work for everybody. We also used Temporal Templates Plus. There's a little extra stuff that we used. It's all in the paper if you wanted to read about it, the Presence paper. And then there was a little interesting, cool thing in Interact. Well, here, I'll just get this started. Okay, so here we have the last bit where the monsters are teaching the last two of the moves. There are only four of them. First, he teaches the kid to do a crouch, and then she does her crouch in response, and he's praising how well she's doing these crouches, and that's great. We go to the point where he's teaching her to do these flapping motions, and you can see he's pleased with her, and he's giving her lots of good feedback. And then I think the last one he's going to teach her how to do is how to spin. He says something like, "Surely love to do a spin," and ready, spin, dude. There he goes. He's spinning, and now she starts spinning, and compliments her on that. And when the music changes, basically they're supposed to do their own moves, and the monsters will follow them. But it takes them a little while to catch on, and from now on, he's following her. Now, one of the things that we did in order to make this room look a lot smarter, the monster would say what you're doing, right? And when it would recognize it, but it only did that when it was sure it was right. If it was close, maybe you're spinning, maybe you're flapping, it would just do whichever one it thought was right. But it would only say it if it was sure. And the reason is, if a monster goes and does something that's not what you're doing, what do? You say, oh, he wanted to do something else. You just ascribe intentionality to the character. But if he says, oh, really cool spin, and you're flapping, he just looks stupid. So the way you avoid this interactive system from looking stupid is it only speaks when it's sure, and it acts all the time because you'll ascribe intentionality. We wrote that up in the paper. It was kind of a cool insight in terms of how to build interactive characters.